Somewhere in the sky above the Atacama Desert, a camera the size of a small car just opened its eye for the first time, and what it saw should not have been possible. Not a new planet, not a comet, something stranger. A smear of ancient starlight so faint that every telescope before it had looked directly at the place it was hiding and seen nothing at all. For decades, astronomers have quietly admitted a truth they don't put in the headlines. Our galaxy is not alone, and it is not what we think it is. The Milky Way should be surrounded by dozens of companions, drifting in the dark like moths around a porch light, bound to us by gravity for billions of years. We can only find a fraction of them. The rest are missing, not destroyed, not imaginary. Missing, the way a person can be missing, presumed to exist unaccounted for. Somewhere just past the edge of what our eyes can reach. And now, for the first time in the history of astronomy, we may have built an instrument sharp enough to go looking. It has been repeated across timelines and video thumbnails over the past few days, and it is the kind of sentence built to stop a thumb mid-scroll. But before we go any further, we owe you the truth, because the truth here is stranger and more exciting than the headline that started this. No confirmed ghost galaxy has been announced inside or orbiting the Milky Way by the Rubin Observatory. Not yet. What has actually happened is bigger than a single discovery. An entire hidden category of the universe, objects so faint they were functionally invisible to every telescope humanity has ever built, has just come within reach for the first time. And the story of how we got here, what Rubin has already found, and what it is about to find, is one of the most quietly staggering developments in modern astronomy. This is that story. To understand why a ghost galaxy is even a real scientific term and not science fiction, you have to understand a problem that has haunted cosmologists for 30 years, a problem so persistent it has a name, the missing satellite problem. Our best model of the universe, called lambda cold dark matter, describes a cosmos built from a scaffolding we cannot see. Ordinary matter, stars, planets, people, every atom and every living thing makes up roughly 5% of everything that exists. Dark energy, the mysterious force accelerating the expansion of the universe, makes up around 70%. The remaining quarter is dark matter, an invisible substance that neither reflects nor emits light, detectable only through its gravity, and it is the true architect of galaxies. According to this model, galaxies like the Milky Way don't simply form in empty space, form inside enormous, invisible halos of dark matter, and those halos are not smooth. Point our telescopes at the sky, and we find about 60, not dozens upon dozens. 60, for 30 years. That gap between prediction and observation has been one of two things. Proof that our understanding of dark matter is fundamentally wrong, or proof that the missing galaxies are out there and we simply cannot see them. It's the second possibility that has just become terrifyingly plausible, and the reason is almost poetic. The Milky Way itself may be devouring its own children. To grasp how strange dark matter really is, it helps to remember how we found it in the first place, because the story fits this same pattern of something hiding in plain sight. In the 1970s, an astronomer named Vera Rubin, the woman this very observatory is now named after, was measuring how fast stars orbit at the outer edges of spiral galaxies. By every law of physics known at the time, stars far from a galaxy's bright center should orbit slowly, the same way Pluto crawls around the sun, far more sluggishly than Mercury does. Instead, Rubin found something that shouldn't have been possible. The outer stars were moving just as fast as the inner ones, as if some vast, invisible reservoir of mass were wrapped around the entire galaxy, holding it together with gravity no telescope could photograph. She had found the fingerprints of dark matter without ever seeing dark matter itself. 50 years later, the observatory built to carry her name is now hunting for the smallest, faintest, most fragile pieces of that same invisible architecture, the shredded halos of galaxies almost erased from existence, waiting to be caught in the act of disappearing. In July of 2025, a team of cosmologists at Durham University, led by researcher Isabel Santos, alongside veteran dark matter physicist Carlos Frank, unveiled a new technique that changed the shape of this problem entirely. They combined the highest resolution dark matter simulation of a Milky Way-like galaxy ever built, known as the Aquarius simulation, with a sophisticated model of galaxy formation called GALFRM. and something extraordinary emerged from the data. The missing satellites weren't missing because they never existed. They were missing because our own galaxy had been quietly stripping them bare for billions of years. As a small dwarf galaxy drifts too close to the Milky Way, our galaxy's gravity begins to peel away its outer dark matter halo, layer by layer, orbit by orbit, like a tide slowly eroding a sandcastle. Most computer simulations, limited by resolution, simply lose track of these battered survivors and erase them from the model entirely, as if they had been destroyed. But the Durham team's more precise technique tracked what actually happens to these fragments across nearly the entire age of the universe, and the survivors don't disappear. They persist. Stripped of most of their dark matter, stripped of most of their stars, they become almost nothing, dim, fragile, and nearly transparent to our instruments. Ghosts. The team's simulations predicted that as many as 80 to 100 of these orphaned ghost galaxies could be orbiting the Milky Way right now at close range, hiding in plain sight. If confirmed, it would not just solve a 30-year mystery. It would be one of the most powerful validations of the dark matter model ever recorded. Because these ghost galaxies aren't a prediction anyone made up to be convenient. They are a direct, falsifiable consequence of how gravity is supposed to work in a universe built on invisible matter. Find them, and the model survives. Fail to find them, and something we think we understand about the architecture of the cosmos may be broken. There was just one problem. Predicting 80 to 100 ghosts is easy. Building a telescope capable of actually seeing something with almost no light, almost no mass, almost no size, is a different challenge entirely. And this is where the Rubin Observatory enters the story. Perched at 8,684 feet on Cerro Pachón in the Chilean Andes, Rubin Observatory is not a conventional telescope chasing a single target across a still night sky. It is something closer to a machine built to film the entire universe as a movie rather than a photograph. At its heart sits the LSST camera, the largest digital camera ever. Constructed for astronomy, a 3.2 gigapixel eye so vast that a single one of its images, printed at full resolution, would need 40 ultra-high-definition television screens just to display it. Bolted to the observatory's 8.4-meter Simonia survey telescope, this camera is designed for one central mission, the legacy survey of space and time. A 10-year campaign to photograph the entire visible southern sky, over and over, roughly every 3 nights, for a decade.
By the time it's finished,
Rubin will have captured more than 20 billion galaxies and 17 billion stars in the Milky Way alone, along with an expected 10 million exploding supernova.
Chief scientist Tony Tyson has described the project as building a digital color motion picture of the universe, a phrase that sounds almost modest next to what it will actually achieve. Crucially, unlike almost every telescope before it, Rubin isn't just built to see things that are bright, it's built to catch things that are barely there at all. Faint smudges of ancient starlight so dim that a single deep exposure from an older instrument would have washed them into invisibility. Picture what that actually means, standing on that mountaintop as the dome slides open at dusk. Most observatories in history have worked like a photographer trying to capture one perfect portrait, a single subject. Carefully framed, painstakingly exposed, Rubin works like a director filming an entire city in motion, all at once, every few nights, for 10 straight years. Each exposure covers a patch of sky 45 times larger than the full moon. Every few nights, that same patch is revisited, and the new image is laid directly over the old one, searching for anything that has moved, brightened, dimmed, or subtly shifted its shape. Multiply that process across the entire visible southern sky, repeated hundreds of times over a decade, and you get something no human astronomer could ever produce by hand, a genuine time-lapse of the universe, deep enough to catch a whisper of starlight and patient enough to notice when that whisper trembles. We didn't have to wait for the 10-year survey to see proof that this design works. In June of 2025, before its official science mission had even begun, Rubin Observatory released its first test images to the public, and buried inside one of them, astronomers found something nobody was looking for. The image captured the Virgo cluster, a dense gathering of galaxies roughly 55 million light-years from Earth. containing more than 10 million individually resolved galaxies in a single frame. In the corner of that frame sat Messier 61, a well-studied barred spiral galaxy that astronomers had photographed and catalogued for decades. It should have held no more secrets. And yet, when researchers filtered the excess light out of Rubin's raw data, a razor-thin stream of stars appeared, arcing away from the galaxy's edge like a scar nobody had noticed before. Astrophysicist Sarah Pearson, who studies these structures at the University of Copenhagen, called it the first stellar stream ever detected by Rubin and stressed that it was only a precursor for everything the observatory would eventually find. The stream stretched an almost unbelievable 163,000 light-years, comparable to the entire width of the Milky Way itself, making it longer than most stellar streams ever catalogued around any galaxy in the observable universe. Its likely origin was chilling in its simplicity. A smaller dwarf galaxy had once wandered too close to Messier 61, and over time that galaxy's gravity tore its smaller companion apart, scattering its stars into a long glowing ribbon now drifting through intergalactic space. The astronomers who published the discovery didn't hide their excitement. They wrote that it was remarkable this feature had gone unnoticed for so long around one of the most photographed galaxies in the sky, and predicted that Rubin would soon uncover what they called a treasure trove of similar hidden structures around galaxies everywhere it looked. There is something almost cinematic about the fact that this happened during a test run. Rubin's official 10-year legacy survey of space and time hadn't even begun. Engineers were still calibrating filters, still checking focus, still running the kind of routine diagnostics that, on any other instrument, would never make headlines. And in the middle of that mundane checklist, buried in a corner of an image nobody was scrutinizing for anything unusual, sat a scar of destruction stretching further than the width of our entire galaxy. Sit with that for a moment. This wasn't even the survey. This was the equipment being switched on for the first time, essentially a test exposure. And it immediately exposed a scar of destruction, more than 100,000 light-years long, that had been sitting undetected in one of the best-studied patches of sky in modern astronomy. If a telescope can find that by accident, in its opening seconds of operation, the question stops being whether it will find hidden ghost galaxies around our own Milky Way. The question becomes when. Stellar streams like the one wrapped around Messier 61 are, in a sense, crime scene evidence. A dwarf galaxy doesn't die quickly, dies slowly, over hundreds of millions of years. As a larger galaxy's gravity pulls at it a little more with every orbit, peeling stars away, in long, thin ribbons that stretch and stretch until the galaxy that once held them together simply stops existing as a coherent object. Scientists studying these structures now believe this isn't a rare event. It may be closer to universal. Sarah Pearson's team noted that every single galaxy should, in theory, be surrounded by streams like this one, evidence of a long and violent history of consumption written in threads of starlight too faint for most cameras to register. If that's true of Messier 61, 55 million light-years away, it is almost certainly true of our own galaxy, far closer, far better positioned. And now, sitting directly beneath Rubin's camera, every single night it operates, and the wind may be closer than you think. In April of 2026, astronomers using data adjacent to this new generation of deep sky surveys confirmed the existence of an object designated CDG-2, an almost impossibly faint galaxy that appears to be composed of roughly 99% dark matter. Only the faintest trace of stars, concentrated in ancient globular clusters, betrayed that anything was there at all. CDG-2 isn't orbiting the Milky Way. It's a separate, distant system, discovered using the kind of subtle statistical fingerprinting, hunting for clusters of ancient stars rather than the galaxy's glow. Itself that astronomers now believe could be turned on our own galactic neighborhood, it is proof of concept.
Ow.
Proof that galaxies built almost entirely from invisible matter, holding on to barely a whisper of visible starlight, are not a theoretical curiosity. They are real, they exist, and we now have a method for finding them. Every one of the Durham team's 80 to 100 predicted orphan galaxies could look something like this: a handful of ancient stars, clinging to the edge of visibility, embedded in a stripped and nearly vanished halo of dark matter, drifting somewhere in the space between us and the edge of our galaxy's gravitational reach. Rubin will not be hunting alone. The European Space Agency's Euclid mission is already mapping vast portions of the sky with a precision built, specifically to trace the invisible skeleton of dark matter across billions of light-years. NASA's Nancy Grace Roman Space Telescope, expected to launch in the coming years, is being designed to push that effort even further from orbit, unblinking, above the distortion of Earth's atmosphere. Astronomers are increasingly turning to machine learning and statistical pattern recognition to do what the human eye simply cannot, sifting through hundreds of millions of data points not for a galaxy's glow, but for the subtle, telltale clustering of ancient stars that gives a nearly invisible galaxy away, the same needle-ina. Haystack method that first revealed CDG-2. Layer these instruments together, and you get something close to a coordinated, decade-long manhunt for the missing architecture of the universe. With Rubin Observatory positioned as the widest, fastest, and most relentless set of eyes in that search, this is where the story widens, because the hidden universe doesn't stop at the edge of our satellite system. In November of 2025, astronomers mapping the region behind the Milky Way's dense stellar disk, a notoriously difficult zone nicknamed the Zone of Avoidance, because our own galaxies, stars, and dust block the view like fog over a highway, discovered something almost too large to comprehend. Hidden directly behind the plane of our galaxy sat an enormous galaxy supercluster, one of the largest structures ever mapped, with an estimated mass of 30,000 trillion times that of our Sun. It had been there the entire time, every night of every year of human civilization. That structure sat behind the glow of our own galaxy's stars. We simply could not see through the light in front of it to notice the giant in the shadows. If something of that scale, 30,000 trillion solar masses, can hide behind our own galactic disk without detection until now, it forces a humbling question. What else has the light of our own home been quietly hiding from us? And here is where the story earns its reversal. The moment where the picture flips and the stakes get larger than a single galaxy or a single telescope. This was never just about finding some faint smudges near the Milky Way to satisfy scientific curiosity. This is a direct test of what reality is made of. If Rubin Observatory spends the next decade sweeping the southern sky and finds these 80 to 100 predicted ghost galaxies clinging to the edge of our own gravitational shadow, exactly where the simulations say they should be, it becomes one of the most powerful confirmations in the history of physics that dark matter is real, structured, and behaves exactly as our models predict, even though we have never directly touched it or seen it glow. Carlos Frank, the physicist behind the original prediction, put it plainly. If the population of very faint satellites his team predicted is discovered with new data, it would be a remarkable validation of the entire theory of galaxy formation as we understand it. But if the decade passes and Rubin's extraordinary sensitivity comes up empty, and those 80 to 100 ghosts simply are not there, then something is wrong. Not with our telescopes, but with our fundamental understanding of what holds galaxies and the universe itself together. Either outcome rewrites a chapter of cosmology. There is no boring version of this story. This is precisely why Rubin's design goes far beyond taking one deep photograph and calling it finished. Beginning later this year, the observatory moves into a new operational phase, built around difference imaging. Comparing each new exposure of the sky against a master reference image, then automatically flagging anything that has changed. A star that flares, an asteroid that drifts across the frame, a faint stream of stars that shifts subtly against the backdrop of a galaxy it's being torn from. Once fully operational, this system is expected to generate around 7 million automated alerts every single night, each one flagging a potential change somewhere across the visible sky, instantly routed to astronomers. For follow-up, it is, in effect, a planetary-scale alarm system for the changing universe, built specifically to catch faint, moving, evolving structures, the exact kind of subtle disturbance a ghost galaxy would make as gravity slowly unravels it. In August of 2026, Rubin released its first major science-grade image built for this new era, a deep look at the cosmos field, a patch of sky studied for more than 2 decades, because it faces away from the crowded plane of our own galaxy, giving astronomers an unusually clear window outward. That single-coded image, built from hundreds of individual exposures collected between April of 2025 and January of 2026, contained more than 650,000 galaxies and over 50,000 stars. It is being described by the observatory's own scientists, not as a finished result, but as a preview, a demonstration of what a full decade of this repeated, relentless imaging can eventually reveal. Rubin, Deputy Director Phil Marshall, has called the Cosmos Field an especially valuable testing ground precisely because of its decades of prior observation, a place scientists already know intimately, which makes it the perfect proving ground to show what deeper, wider, more patient imaging can add to a picture we thought was already complete. That is the quiet theme running through every single one of Rubin's early results. Nothing it has looked at so far was truly new territory. Virgo had been photographed for a century. Messier 61 had been catalogued for decades. The Cosmos Field had already logged more prior observing hours than almost any patch of sky in existence. And in every single case, Rubin found something none of those previous instruments had ever managed to see. If that is what happens when Rubin points its camera at the places we already thought we understood, it is worth asking, with real unease and real excitement. What happens when it finally turns that same unflinching gaze toward the quiet, familiar darkness immediately surrounding our own galaxy? Zoom out even further, and the pattern doesn't stop at our own galactic backyard. Astronomers already know the Milky Way itself carries the scars of this same violence. The Sagittarius Dwarf Elliptical Galaxy, a small satellite that has been slamming through our galaxy's disk in a slow, repeating collision for billions of years, is thought to have triggered ripples that help sculpt the Milky Way's own spiral. Arms, meaning some of the very structure that makes our galaxy beautiful, may exist because of a smaller galaxy we have been quietly consuming the entire time. Widen the frame past our galaxy entirely, out to the Virgo cluster 55 million light-years away. And Rubin's very first image showed the same violence playing out around Messier 61. Widen it again, out past the local group into the vast supercluster hidden directly behind our own galactic disk in the zone of avoidance. And you find another 30,000 trillion solar masses of structure that spent all of human history sitting unseen in our own blind spot every